Okay, so what we were doing though, we were looking at this this burn-up rate. So doubling the number of gigawatt hours per ton of uranium would give, so it would half the spent fuel production. So you're getting, double the amount of energy out of the same amount of fuel, and then give up to a 6.5 reduction in the fuel going in. So you're just using more of it up. It's not like only half goes in. It's just that you're getting a lot more bang for your buck out of what's in there. But the high burnup may not be without costs. The burnup of 100 gigawatt days per ton would require the use of uranium enriched to a greater amount, so up to 10%. So back to the question, like, when do you stop enriching? So the whole life cycle has to be looked at. And there's one little thing that says, what determines the burnup of a reactor? This is important to realize that any given burnup necessarily implies a certain degree of enrichment. Obviously, if the number of fissile atoms in each ton is increased, fewer tons are needed, obviously. So the burnup rises. It should also be borne in mind that greater enrichment means mining more ore. Yeah, so it's kind of a zero-sum game in a lot of ways. The second factor is the time that it spends in the reactor. The longer the time, the more uranium is likely to be used up. Also, energy from the fission of the plutonium that is always bred in the reactor can be significant. With each batch of fuel spending a few years in the reactor, plutonium contributes slightly less than half the total energy produced. It says, however, the rate of breeding of plutonium decreases after a few years. So at some point, as this, as the uranium reaction occurs, the amount of plutonium there increases. The plutonium itself starts to diminish, and therefore you're getting more burnup because there's less of that around as well. So there's different phases and cycles of what atoms are in there. And as it says here, these fuel rods can be in there for years. Okay. How are we doing on time here? Nuclear power and safety. Yeah, let's just go through this one last section on safety, and then I want to do a few things on the summaries before I let you go. So, okay. Last little bit, 11.6, nuclear power and safety. Now, this is true. No energy technology is completely safe. And, gosh, take it all the way back to the horse. People die falling off of horses. That was probably one of the first. Or the campfire, right? People, died in that as well. And really, the way I look at these things are that any energy technology is operating at some distance from thermodynamic equilibrium, meaning that, what's the best way to describe that? Simplest way to describe it. I don't want to get too philosophical here, but we take it all the way back to potential and kinetic energy, right? So I've got my rock sitting at the top of the hill, E equals mgh, right? Push it down, and who knows? Maybe this is actually going to do some work for me. Maybe it's going to defend my village. Maybe it's going to knock a tree in half. Maybe it's going to bust down a house so I can get some remodeling done. Anyway, it's going to do some work for me, right? At the bottom, it's going to be E equals 1/2 mv squared, cruising along, and then it's just going to kind of rock back and forth until it's just kind of sitting here doing nothing when phi equals 0. It's now in equilibrium, right? All of its energy's gone, it's just kind of sitting there. So, same thing is true once all the nuclear fuel is gone. Same thing is true once the petroleum. In a lot of ways, all of our energy technologies are sort of just knocking that rock from the mountain to the valley. We're taking our planet closer to a thermodynamic equilibrium. Very first sentence here, no energy technology is completely safe. Why is that? Well, because in every case, the rock's sitting at the top of the hill. The uranium gets concentrated. The oil gets made. The gasoline gets made. These are all high concentration of energy, very far from thermodynamic equilibrium. Not something you're just going to find laying around in nature. We've refined this, and we've purposefully made things. I don't want to say dangerous, but we've made things energetic. We made them more energetic, more powerful, so that we can get more work out of them. Okay, that's enough philosophizing. Now, to the question of whether or not nuclear power is safer than any other energy technology is hotly debated, and will be discussed later in chapter 13. Okay, now, and there are different ways for nuclear facilities to fail. One is if something breaks, so malfunction of a plant, poor design, construction errors, human errors, Fukushima, natural disaster. You might say, well, gosh, they could have built the thing better. Well, yeah, maybe, but heck, at what cost, right? Okay. Another way it could fail, deliberate military attack. Cyber attack is not out of the question. There's not a guy sitting in there with a bunch of, there are levers and buttons, mind you, but a computer program runs the facility. So if a bug in the software and someone said, pull the rods out, don't shove the rods in. It's just a binary flip of a switch, right? It's just on or off, and the whole thing is reversed and unstable. Okay. Now, what are the things that actually make this, make these things dangerous? Iodine leaking out, cesium leaking out, strontium leaking out. Let's take a look at these on the periodic table. Yeah.
So it gives you energy?
Well, no. Actually, no, I want to look up the dynamic periodic table.
No, potassium's supposed to do for it?
Well, potassium is an ion. So in your nervous system, for example, you've got potassium ions and sodium ions, and they are constantly being pumped back and forth through little channels in your nerves. And which one is similar to potassium, does it say?
Cesium.
The cesium? Yeah, let's take a look at that. So here's, exactly. Here's potassium right here. And if we take a look at the orbitals, this is the easiest way for me to look at them. Potassium's got that one up orbital in the 4s, one up electron in the 4s orbital. And so if we come down here to cesium, it's the same thing. So chemically, potassium and cesium look like each other, and the cesium will go in there as a fake and say, oh yeah, I'm potassium hanging out doing my thing, but it's more massive, and if it's radioactive, it's firing off these different particles that we mentioned and messing with your DNA, blasting holes in your DNA. Strontium, let's look for that guy.
So they're not a substitute for bananas.
What's that?
Cesium's not a substitute for bananas.
No, I wouldn't know what you're cesium banana in the morning, no, not a good idea.
Doesn't help if I'm cranky.
Guys, help me find strontium here really quickly. It's funny, like back in the day, you just like, you know these things, and then they leak out. 38, there it is, okay. Strontium, oh, you always hear about strontium in your bones. Same deal, so strontium looks a heck of a lot like calcium right there. So that's the connection. And then iodine, well, you know, iodine also resembles chlorine. Your body does, in fact, use iodine. There are proteins that bind iodine, just like their hemoglobin binds iron. And so, in fact, I want to take a look at this. There's a video out there online. So with the proper imaging software on your satellite, how do you spell Fukushima?
They add iodine as salt.
UKU.
Yeah,
It's difficult for us to get it, so.
well, yeah, so iodine, so there's iodized salt, and it's just a way for somebody to get salt that wouldn't maybe get it from a fish, you know, from eating fish, for example. Yeah, so one of these guys has there's a little movie. I need to save a copy at some point.
You looking at new trucks or something? Expanding the trucks. Yeah.
That's terrible. Let me see if I can go over here. I think there's a video out there. Oh, here we go. This is the one. So this, okay, so this is April. Okay. So this is just, you know, showing iodine and weather patterns. And I don't know if you guys remember, but in around this time, people in California were going out and buying a lot of iodine. And the idea is if you can sort of saturate your body with non-radioactive iodine, but then iodine, you ingest it somehow, it'll just pass through more.
Because you're not deficient on it.
Right, exactly, because you wouldn't be deficient.
Makes sense.
Yeah. Anyway, okay, so there's that. All right, so a few other things. 3 Mile Island, 1979. Winsdale, 1957. I don't know if that has any correlation with what we saw previously with demand. This is getting later in the, oh, here. Oh, you know what? Right there's the wind scale accident. 79. There's just a little blip there. Let's see, 60, 70, 79. Yeah, that's right. There we go. I mean, that's right around 1980. That's the 3 Mile Island, right there. This was Chernobyl. It's sort of already on its way down and just kind of kept going down. And then Fukushima is, you know, not really on here, so we don't really have that data yet. But okay, and then there's a couple shots of what happened. This is the section through the boiled water reactor, and then the damage from the hydrogen explosion. Yeah, so they actually had a meltdown. Once the water was gone, so once the water leaked away, it's not there to cool it, and it just went into a runaway meltdown. 200,000 people evacuated. Man, that's a lot. Okay. All right. One quick thing, and then we'll wrap it up here. And I just want to say this for the general audience. So, on your summaries, this just a couple things on your summaries. What we're not seeing all the time. You definitely need to have your citation in the document. And now I realize there's only one paper you're reading, but you still need to cite it. It's required. It's good practice. So author, year. If you use the author's name in a sentence, you can just write author, and then in parens put the year. Either one is fine, but be sure you do that. Also, write the bibliographic information at the end of the document. So author, year, title, volume, issue, page number. If the issue's not there, it's not that big a deal, but just check the boxes, just so it's not distracting. I'd much rather focus on your writing. Other than that, I think the summaries are coming along pretty well. I resent the videos on how to do your summary 3, format the Excel, copy it as a image into Microsoft Word, put the figure captions in, and it's going to be great. I mean, it's a really good exercise for just making you more efficient and effective at writing papers down the road. So your future employer will thank me. Oh my God, what a beautiful report. All right, guys.
I mean, we have to cite you at the bottom.
Yeah, no, well, the citation is the AAS after your degree, after your name. That's your citation. All right, and also for anyone else out there listening in 101, if you're taking 101, chances are you need to put in a graduation application for your certificate in the spring.
When's that due by?
Well, the spring applications were already due. They're still accepting them with the...
I think they're accepted late until like January.
Yeah. But also chances are if you're an NRGY 101, you're going to take the practicum, which means you're not going to graduate until summer anyway. The summer graduations aren't due until February. So if you're in 101 in the fall semester, chances are, and you're taking a full load, chances are you're going to want to put in that certificate. The main hall really wants to see that. The Board of Regents is really breathing down the University of Montana's neck in terms of enrollment, graduation, the whole thing. Like, you guys aren't doing your job over there. Why are we giving you? Why we're going to write you out of the tax bill? So. And all that.
People are scheduled to graduate.
Yeah, and all that's right. They just want to see that we've got, got guys.
I think the deadline for the summer is not until March.
Yeah, I think Naomi said February. So yeah, but anyway, just so a couple things to note on your summaries. Also, one last thing on your summary. Be sure to put that catchy title in. I don't think I put that in the official rules, but
I think you told that on the first one.
I did.
So every time I start a paper and I don't have a title yet, I just put
catchy title. There you go.
I just give a title at the end.
That's the time to do it. Yeah, when you're done and you've got the whole summary kind of in your head, a title will just pop right. All right, guys. Thanks a lot. It's a good time.